Welcome to the deep dive. Today, we're exploring a really fascinating question. How well do we actually understand our own planet?
And maybe more importantly, what happens when our knowledge is, well, dangerously incomplete.
Exactly. We've got something pretty thought-provoking lined up. We're going to start with this gripping piece of science fiction.
Kind of warning, right?
Yeah, a warning about the dangers of not knowing enough, and it feels unsettlingly real sometimes.
Mm.
And then we'll pivot. We'll look at the cutting-edge science happening right now.
Earth system models.
Yeah.
ESMs.
Right. We'll see how actual scientists are trying to avoid that kind of fictional disaster scenario.
It's amazing, really, how a fictional story can highlight the real challenges we face, even with today's science. In understanding Earth's complexity, I mean.
It really is. It's like a powerful thought experiment about what we might be missing. So our mission today is basically to pull out the key insights from both the fiction and the science, give you a shortcut to understanding the risks of, let's say, oversimplification, but also the incredible work being done in climate science.
Okay, let's do it.
Right. So let's start with the fiction. We're diving into excerpts from a story called The Severed Web by Job Roberts.
And just to be clear up front, this is science fiction. It didn't happen.
Correct. It's a speculative scenario, but wow, it asks some big questions about, the limits of what we can see and how we interact with the planet.
So what's the setup?
Okay. It introduces Dr. Elena Vasquez. This is years after some big global event called the Convergence Chamber. She's surveying this really desolate landscape.
Where is she?
Iowa, apparently. It used to be
Yeah.
this vibrant regenerative farm, but now just cracked, barren earth, dead.
Rhea.
And right in the middle of it all stands this thing called the terrestrial flux converter. It's described as sleek, elegant, humming with energy.
And what does it do?
It delivers clean power, perfectly efficient, a monument to human hubris, the story calls it.
Okay, I see where this might be going.
Well, here's where it gets really interesting. The kicker, as they say.
Go on.
The device works exactly as designed, flawlessly,
Wow.
but that's the problem.
Right, the unintended consequences.
Precisely. Elena gets her AI, called ARA, to run a subsurface analysis, and the results are, well, catastrophic.
What does it find?
The mycorrhizal biomass, those crucial fungal networks in the soil,
Yeah, vital for ecosystems.
it's down to 0.02% of baseline levels, basically gone in the upper layers.
Wow. Okay.
But then ARA finds something else, something deeper, something unexpected. The display shows these vast fungal networks extending way, way down.
Deeper than they thought.
Oh yeah, down to 800 meters. Their simulations only ever went down to maybe 15 meters.
800 meters. That is incredibly deep.
Exactly. And Elena realizes these weren't just surface things. They were like a planetary nervous system.
The planetary nervous system. What does that even mean in this context?
Well, the story says they were integral to geological stability. They interfaced with mineral cycling, groundwater, even, get this, tectonic stress distribution.
Okay, hold on. So the fiction is suggesting that deep fungal networks influence tectonic stress. That's a pretty wild idea.
It is, and it really raises that central question, doesn't it? What happens when your understanding, your models, are based on incomplete observations, even if the math for what you can see is perfect?
Yeah, that's a profound challenge. The known unknowns, and maybe even the unknown unknowns.
And the story gives a chilling answer. Elena has ARIA, overlay seismic data, earthquake patterns from the last 10 years, with the locations of these flux converters.
And there's a match.
A direct, unmistakable correlation. Wherever these deep networks were severed by the converters, there's unprecedented geological instability. Earthquakes, fissures.
A cascade effect.
Totally.
Yeah.
Disrupting mineral flows, shifting groundwater, cracking the actual rock formations deep down.
So the takeaway from the story is really about the data, isn't it? Not just the equations.
Exactly. Perfect math, but incomplete data. It's a stark reminder that what we don't observe, what we can't measure yet, might be the most critical piece.
And that's where the story really lands its punch, I think. Showing that catastrophic ripple effect just from missing one fundamental layer, these deep biological networks.
It didn't matter how sophisticated their surface models were.
No. The story mentions the Gaia Complex's simulations. They were described as beautiful, complex, sophisticated.
But totally blind to these deep Earth processes.
Right, because their instruments could only see the surface stuff. These deep networks operated below our detection thresholds, dealing with quantum scale interaction.
Quantum scale, what does the story suggest by that?
It implies these really subtle, maybe foundational energy exchanges, things way below what their standard sensors could pick up, but somehow vital for the planet's deeper stability.
And their big project, the ethereal weave, it worked perfectly in the simulation.
Yeah, because, and this is the key quote, the simulation was accurate for everything we could observe.
Wow. So they literally built their future on models that were perfect for the slice of Earth they could see.
While completely missing this vast, hidden biological infrastructure underneath.
It's like building this amazing house, perfect blueprints, perfect engineering for the visible structure.
But you didn't realize it was sitting on this incredibly complex living root system that was essential for the ground stability, and your foundations just cut right through it.
Yeah, that's a really good analogy.
And connecting that back to real science, while we've obviously come incredibly far, there are always elements we're still figuring out, right? The deep ocean, subsurface
Yeah,
microbes. We're still mapping those unknowns.
sure.
But I think a key difference is that modern science tries to acknowledge and quantify that uncertainty. We don't generally assume we have the complete picture. There's ideally more humility there.
Which is something the characters in the story lacked until it was too late. Dr. Vasquez has this heartbreaking realization. She says something like, "We're discovering our most advanced equations weren't enough. We've been using math for simple systems to manage a quantum biological planet."
Oof, that is hard.
And then the choice she faces is just tragic. Shut down the converters, cause a global power grid collapse, mass chaos, estimated casualties.
Or keep them running and continue destroying these vital, hidden planetary systems they just discovered.
Yeah. The story ends with this advanced civilization realizing Earth was way more complex than their instruments could see.
And they learned it too late.
Chilling stuff, really makes you think.
It absolutely does. A very effective cautionary tale.
Okay, so that was the science fiction. Powerful warning, definitely fictional. But now, let's ground ourselves. Let's talk reality.
Right. Let's look at where we actually are today with Earth system models, the ESMs. How are real scientists trying to avoid that kind of severed web scenario? How do we try not to miss the crucial puzzle pieces?
Good question. To get ESMs, we kind of need to see how they evolved, right? Where did we start?
Absolutely. We started back in the 1960s, really, with early climate models. They were mostly called general circulation models, or GCMs.
And what did they focus on?
The real basics. Fundamental physics, atmosphere, oceans, how air and water move, thermodynamics, radiation, the big physical drivers.
How did they actually do that? Computationally.
Well, they treated the Earth as a grid. Like, imagine dividing the planet's surface and atmosphere into 3D boxes.
Okay.
And then they use equations to calculate how energy, heat, moisture move between these boxes over time.
So like a basic sketch of the Earth's climate engine. A fantastic start, I guess.
A huge start, foundational work, but yeah, pretty simplified compared to now. As computers got way more powerful, the ambition grew.
They started adding more pieces.
Exactly. They started coupling components. The first big step was linking atmosphere and ocean models together. Atmosphere-ocean coupled models.
Why was that so important?
Crucial for simulating things like El Nino. You absolutely need the ocean-atmosphere interaction to understand that. You can't treat them separately.
Makes sense. What came next?
Then came land surfaces, vegetation, and ice, the cryosphere, as it's called.
So adding things like how reflective ice is, the albedo effect.
Right? And snowmelt, how water cycles through land, how vegetation influences moisture, all getting more realistic.
Okay, so that brings us closer to modern ESMs. What's the big leap they represent?
Well, I think what's really fascinating is how ESMs go far beyond just the physics. They integrate complex biogeochemical cycles. This is where we're really striving for that more complete picture the fiction warned us about missing.
Like the carbon cycle.
Exactly.
Yeah.
It's not just treated as a fixed input anymore.
Mm.
ESMs simulate how CO2 is actually absorbed and released by oceans, by land, by plants.
So they can model feedbacks.
Yes, critical feedbacks. Like a warmer ocean absorbs less CO2. That leaves more CO2 in the atmosphere, which causes more warming. ESMs try to capture that loop.
What is in these modern models?
Oh, lots. Aerosols, those tiny particles in the atmosphere, dust, pollutants, sea salt.
They matter.
Hugely.
Yeah.
And they're complex. They can cool or warm the planet. And their interaction with clouds is actually one of the biggest sources of uncertainty in climate projections right now.
Hmm.
ESMs try to model their formation, their chemistry, their effects.
Okay. What about life? Plants.
Yep, dynamic vegetation. So the models don't just assume forests stay where they are. They simulate how vegetation might change over time because of climate change, like forests moving northward as it warms, for example, or changing types of vegetation. And that, of course, affects the carbon cycle, water cycles, albedo. It's all interconnected.
Wow. It's getting incredibly complex.
It is. And some of the most advanced models are even starting to integrate human systems more directly. Things like land use changes, agriculture, deforestation patterns, trying to get really detailed projections.
It sounds amazingly comprehensive, but I mean, building these for the entire planet, that must be just a monster computational challenge, right? All those interconnected systems.
Oh, absolutely huge.
It almost makes you picture the scientists, watching these supercomputers churning away for months, just hoping, please tell me we haven't missed some crucial deep earth fungal network.
Hmm. Well, you joke, but that underlying what if we've missed something fundamental is, I think, what genuinely drives a lot of the scientific effort.
The humility you mentioned.
Exactly. Recognizing there's always more to learn, more to observe, but yeah, computationally, it's immense. Remember that grid system?
Dividing the earth into boxes.
Right. The smaller you make those boxes, the higher the resolution, the more detail you can capture, the more accurate the physics can be.
Wow.
But the computing power needed goes up exponentially. Like doubling the resolution, making the grid cells half the size can easily mean needing 10 times the computing power.
10 times, just for doubling the detail.
Roughly, yeah. Depends on the model, but it's that kind of scaling. So to give you an idea, a single high-resolution simulation, maybe modeling climate for a few decades into the future, that can take months to run. On a supercomputer the size of a tennis court, burning massive amounts of energy, ironically.
Wow. Months on a machine that big.
It's a massive undertaking, which is why international collaboration is so essential.
You mean like different groups sharing their work?
Yeah, there's this project called CMIP, the Coupled Model Intercomparison Project. It's basically an agreement where research centers all over the world run standardized experiments with their different ESMs.
Why standardize?
So you can compare apples to apples, see where the different models agree, where they disagree, what the range of possibilities looks like. It builds confidence and helps pinpoint uncertainties.
And that's the data that feeds into the big reports.
Exactly. The results from CMIP are fundamental to the big assessment reports from the IPCC, the Intergovernmental Panel on Climate Change. They provide that consolidated scientific view.
Okay, so we have this massive global effort, constantly improving models, adding complexity, checking against observations.
And this brings us back to the start, doesn't it?
Yeah, that fictional warning from the severed web.
It really underscores that while we're making incredible strides modeling the systems we know about and pushing our observations deeper and wider,
We always have to ask,
what might we still be missing? At those deeper, less obvious, maybe harder to measure levels, that story emphasizes the scientific humility we need, constantly questioning assumptions.
what a journey we've taken then. From this pretty chilling sci-fi warning about overlooking something fundamental.
To the incredible, complex, real-world effort of building our understanding of Earth with these ESMs.
It really is a testament to, well, human ingenuity and this relentless pursuit of knowledge, isn't it?
It is. And zooming out, thinking about the bigger picture here, it just shows this constant scientific process, right? Always trying to expand our tools, what we could observe.
And then integrating more and more pieces into the puzzle, aiming for that truly comprehensive picture.
It's never really finished. It's always discovery, refinement, pushing those boundaries of what we can actually see and measure.
So wrapping this up for you, our listener, what's the takeaway? The severed web, the fiction, gave us this glimpse of what could happen with perfect math but fatally incomplete data, missing that hidden biological infrastructure.
While the real-world ESMs, they represent this huge global dedication to getting more complete data, to understanding all the intricate connections and feedbacks between atmosphere, ocean, ice, land, life.
Accounting for as many variables as we possibly can.
Yeah.
Moving beyond just the surface and looking for those deeper connections.
Yeah, trying hard not to miss the crucial bits.
So maybe the final thought to leave you with is this. The challenge isn't just about faster computers or more complicated equations. It's also, maybe fundamentally, about continuing to push the boundaries of observation itself.
What can we measure? What can we detect?
Right. What if, like in that story, there are still layers of complexity? Maybe at quantum levels, maybe in deep biological, geological links we haven't even conceived of yet. Things that our best instruments today just aren't designed to see.
It's a humbling thought. How do we keep learning, keep adapting, stay humble? Faced with a planet that just keeps revealing more and more astonishing complexity.
Something to ponder. Until our next deep dive.